Hello and welcome to another tutorial. In this lecture, I'm going to discuss more details the PSO, especially one of the very interesting use cases of PSO, particle swarm optimization. So in the previous lectures, I talked about PSO as a very simple and very elegant approach for minimizing or maximizing or in general optimizing a function. And it could be easily applied to any function with any dimensionality. So the number of variables of the function could be anything. And we mentioned that it's not based on gradient, so it's derivative-less. So we don't need the hassle of calculating the derivatives. So that relaxes a lot of conditions on the function. We don't need the function to be smooth. We don't need any requirements for the derivatives to exist at any particular interval. And we mentioned that the general approach is based on the behavior of a swarm. So there are some members of the swarm, which we call them particles in general, but these particles could represent a general member, so like a bee or an ant in a swarm of bees or ants. And we said that each particle has a random walk, so its motion is basically a random, but then the particles obey the swarm's objective, right? So even though each individual particle has a random behavior, in general the swarm has a particular objective in mind, and we call that objective a fitness function. And that fitness function is basically determines whether we want to maximize or minimize this fitness function. Okay, so the swarm's objective is determined based on the maximization or minimization of a fitness function or a general given function. All right. And we said that, okay, we can update the velocity and the position of particles based on the particle's behavior, or basically these two extra terms, which are the social factors or social behavior of the particle. And the first one is tracing the best path for the particle based on the fitness function. The second one is keeping track of the swarm's behavior. So G represents the group and X represents the individual particle. All right, because we have to have the behavior of the particle, the motion of the particle should be influenced eventually by the behavior of the swarm, right? And we took this algorithm or pseudocode from the Wikipedia, and we exactly implemented this in Java, which was extremely easy, following an object-oriented programming. And then we had some examples of just giving us a very nice intuition of how the particles basically search the space, move into a space, how they in fact converge to a extrema, a maximum or minimum point. And I'm going to play this one more time. So this shows that we have 20 particles and their position or the x coordinates converges eventually to the maximum, and here we had the minimum, and all of the swarm basically converges. And the good thing is that the PSO is immediately scalable to more than one dimensions, but having a nice visualization in more than one dimension or more than two dimensions, let's say, is not that nice. So we can have a very nice visualization of what happens to the particles in one dimensions or two dimensions. But now let's have another, or let's look at another use case, a very interesting use case of particle swarm optimization, which is I'm going to use the PSO for solving equations. So what do I mean by that? Now, we looked at solving equations before, and we implemented all of the common root finding algorithms. So here I'm looking at the one-dimensional case to solve equations, let's say one-dimensional. So f of x is 0, f is a real function, x is a real variable, okay? And we're looking for real roots. So even if the function is real, it might have complex roots. So here we're looking for real roots, all right? And obviously one example is polynomials. Polynomials are take a real number and return a real number, but in fact they could have complex roots. But here I'm just looking at the real roots. All right. Now PSO is a very lightweight optimization routine. It's just a bunch of multiplications, summations, and function evaluations. There is nothing else, and we cannot get away with anything less than this, right? We have to have any root finding algorithm eventually has to evaluate the function, right? We cannot get away with evaluating the function or doing some extra math, extra multiplications or additions, and etc., right? So these are like the basics, the bare minimum that we need. So PSO doesn't doesn't require much heavy calculations or whatever. It's just a bunch of function evaluations and basic math. All right. And we looked at them in the past. We looked at the common root finding algorithms, and they were all based on the root bracketing concept, right? The notion of root bracketing, and the root bracketing was based on the general lemma of root bracketing, which means that if we are searching for the roots of f of x equals 0 over the interval of a and b, then what happens here is that if f of a times f of b is less than 0, this general lemma of root bracketing guarantees that this interval of a and b is a bracket for the root. So there is at least one root in this interval. But the constraint here is that we have to know that the fx is the function f of x is continuous. So the continuity was the condition. So if f of x is not continuous over the a and b interval, the general lemma cannot guarantee that we have at least one root. All right. So continuity was a problem here. And then based on this general lemma, we constructed bisection and trisection, which is basically a binary search or a ternary search, divide and conquer, let's say. So we divide in halves. For bisection, we start with this. We make sure that it's a bracket. So again, the requirements or prerequisite is that the function must be continuous so that we can do bracketing. And then this general lemma guarantees that there is one root. And then bisection is trisection is just a search approach, a recursive search approach for finding the root. So bisection and trisection says that a and b must be a bracket, so continuity is a requirement. But then it also failed. Not only continuity was a requirement, but bisection and trisection failed when the root was a tangent root or an even order root, which means that if we expand the function, if we expand the Taylor series of the function around the root, we end up with the even power, x minus root to some even power, 2, 4, 6, etc. Okay, so at any tangent root, any even tangent root, but tangent, a third order root could also be a tangent. Here we're mainly talking, here the problem is with even tangents. And the problem was that when you have an even tangent, the sign of the function doesn't change around the root, right? Whether or if x is less than r or greater than r, this term is always positive, has the same sign. All right. So again, we cannot find a valid bracket because the bracket relies on the fact that the sign of the function should change. All right. So obviously the bisection and trisection failed, and we looked at different examples that the bisection and trisection, they have this problem. We looked at the secant method, and we improved it, and we looked at the false position method, and we also looked at the Brent method, and these were all based on interpolation. Secant was first order interpolation, Brent was second order interpolation. And then here again the continuity over the interval was the condition or prerequisite, because we have to make sure that the original interval is in fact a bracket for the root. We have to know beforehand that there is a root in the interval so that we can go ahead and apply these methods. All right. So having the continuity of the function was a problem, and knowing that uh, the, basically the A and B interval, the original search interval is a bracket, and again by bracket we try to apply the general lemma, and that only applies, or that only guarantees the existence of a root when the function is continuous. And then we looked at the other methods that required calculating the derivative, which was Newton-Raphson or Newton's method, and we said that these could be faster than the previous ones because they rely on the gradient. But again, when you try to calculate the derivative, you have the condition that the derivative must exist. So that was one problem. The other problem was that f of x equals 0 at some iteration point. So f of xn, let's say, at some step was a problem. So if f of xn at some iteration step, the function, or the f prime, let's say, yeah, if the derivative of the function becomes 0, this was a problem and the Newton-Raphson method fails. So even if the function could be smooth, even if all the derivatives exist, and remember that smoothness requires continuity. So if a function is not continuous, it definitely doesn't have a smooth behavior. There are some points or discontinuity points that the derivative doesn't exist, all right? But even if the derivative exists and the function have a nice behavior, if at some point we hit the f prime equals 0, then the Newton method failed, all right? Now what do we want? We want a root finding algorithm that is very simple, very elegant, and it doesn't have all these problems. So we don't need to find the derivatives, we don't want to do that. We don't want the requirement of the continuity, all right? And we don't even care about whether or not the initial search interval is basically is a bracket or not. We don't care. We want to search the interval. If there is a root, we want to find it. If there are multiple roots, we want to find it. If there is no root, okay, we don't find anything, right? So this continuity, we want our algorithm to doesn't care about the basically continuity of the function, the existence of derivatives. We don't care if the initial search bracket, the search interval is a bracket for the root or not. So none of these problems with all these previous method. So how do we do that? So using PSO, remember PSO was for optimization of a function, so minimizing or maximizing. Now a very interesting thing to observe about the behavior of a function f of x is that if you plot it, if the function has a root, here I'm plotting over the a and b interval, here I'm also assuming that okay, the function is continuous, so it's not required, right? And if the function has a root, it means that it has to cross the x-axis at some point, right? And then what happens here is that the behavior of the function could be two things. One is that the function is actually crossing the horizontal axis, or the function becomes tangent, all right? Positive tangent or negative tangent, doesn't matter. What matters is this observation. If I take the absolute value of f of x, so if I look at the function absolute value of f of x, everything negatives comes up. So if it's tangent, then it keeps the same shape, right? But if it's negative, then it comes up, becomes something like this. Now you see here we're crossing the f-axis, the x-axis, and when we take the absolute value, the function has a non-smooth point here, right? So the derivative doesn't exist at this point because the left derivative and the right derivative are not equal. If it was tangent, then the function is still smooth, right? But again, we don't care about that. What we care about is this observation that when we look at the absolute value of f of x, the root, if the root exists in this a and b interval, it's actually the minimum of this function, absolute value of f of x. So that's a great observation, because now I reduce the problem of finding the root to a problem of finding the minimum of a function. And the PSO is the fastest, or one of the great ways to find the minimum. So initialize the PSO in the a and b interval, set the fitness function to the absolute value of the f of x, f of x is the equation that we're trying to solve. Remember, f of x should be equal to 0. So if you have some terms on the right side, you have to bring them on the left, all right? So the fitness function should be absolute value of f of x. And then we don't need many number of particles. 10 particles should suffice. So we're going to set the number of particles to 10. And then the number of iterations 50 to 100. And again, at each iteration steps, we're not doing anything fancy. We're just evaluating the function for a number of particles, updating the position and velocity, which is just a bunch of additions and multiplications. So we're doing bare minimums to run this algorithm. So we're going to set the number of particles to 10. And the main thing is the objective of the PSO. We have to make sure that we set the objective to minimization, not maximization. Because when we take the absolute value, anything negative comes up, all right? So the objective is minimization, 10 particles, 100 iterations, 100 iteration steps, and the fitness function is absolute value of f of x, all right? So when we do this, we have a great hope that we are able to find the minimum of the function at this interval. But there is one last step, because if the function doesn't cross the x-axis, it means doesn't have any roots. But eventually the PSO is going to return a number as the minimum, as the minimum candidate, let's say, or the candidate minimum. But then finally we have to have a final test for the root. So I'm going to write this here, final test f of mean equals, I'm going to put a question mark to 0, all right? This means that when the PSO finishes and returns a value for the minimum, we have to test whether or not this minimum is actually the root or not, all right? So with all these steps, the PSO should be able to give us the root. And the important thing is that PSO doesn't care about the continuity. PSO doesn't care about the bracket, because eventually we run this test. So it's not part of the PSO. It's just a thing that the user or us as programmers is going to check this condition anyways. All right. So let's head to Eclipse and try to implement this root finding algorithm. So if you recall, we had this demo roots project, and in the demo root project we had this real root function, which represents a one-dimensional real function, and we annotated it with functional interface. So it should only have one abstract method. And then we had this real root class in which we implemented the bisection, trisection with secant, Brent, Newton, and we had a method that tries to find the root in an interval, and also a method to return a list of roots in a given interval based on some number of sub-intervals. And the idea was to divide the original interval into some intervals, and in each sub-interval try to find the root, all right? Now what we're going to do, we're going to do a public double. We're going to write a method to apply the PSO, like PSO root, just PSO double start double end. And here what we're going to do, we're going to create a double root equals double.nan, and eventually we're going to return this root, all right? And what we are going to do here, we're going to create a PSO object, new, and I guess we need to keep a dependency. So if you go to build path, keep a dependency on the projects in the working space. We're going to give a dependency on the PSO project, and here PSO, and we're going to import it. Number of particles 10, fitness function. Okay, fitness function, remember we have to take the absolute value of the function. So t goes to math.abs of real root function, I think we called it func, real root function, dot, I believe it was value t. And recall that here the fitness function for the PSO was an n-dimensional function. So here we have to, because here we're just looking at the one-dimensional function, it should be t of 0. So the first element of t. So t is a vector, all right? And then the intervals, it takes an interval object. So in order to do that, let's go up here and we're going to, from PSO, I'm going to import all the static method, import static PSO, everything, and we go back here. Now interval is a method, a static method, and it's start and end. All right, so now we have this this PSO, and let me just remove this, and it should give an error, and the error says the value expects the method value expects a double, but we are passing an array of doubles because the fitness function interface was defined for an array of elements because it was n-dimensional function. All right, so now we have the PSO, and what we are going to do, so let me just write some notes here. Create PSO 1D, all right, and remember that remember the fitness function is ABS of root function. All right, and then we are going to set the goal of PSO. Remember here we're looking at the set minimize. We're going to make sure that it's true, and then we're going to iterate. So PSO.solve, and we're going to set it for 100 steps of iterations. Get the root or root candidate or the minimum candidate, min candidate, and in the min candidate we're going to do the double root equals, or we already defined the root, so root equals PSO get best value, right? Remember, best position returns the n-dimensional vector that gives the best value. Best value is the value of the fitness function. All right, and here the fitness function, this returns the absolute value of f of x, the function, and basically test the mean. We're going to test the mean. So if math dot ABS of so what we're going to say is that if we have the func dot value and root, okay, is close enough to 0, so if it's greater than 1e minus 9, or the root is basically less than the start, or root is greater than end, we want to ensure that the root is also in the function, because there is a slight chance the particles get out of the interval, because recall that the PSO that we implemented, it wasn't a bound optimization. We say that okay, the particles are initially in this interval, but there is no guarantee that they're going to always stay in this interval. Now there are ways to add these bounds as constraints to the PSO, but right now it's just an unbound optimization. So we're going to make sure that the root is in fact in the interval. So if the function at the root candidate is not close enough to 0, or the root is outside our search interval, we're just going to return a none. Otherwise we take it as the root. All right, so this is how we implement the PSO. And let's go here, and maybe let's also, if you recall, we had for other methods, bisection or trisection, we also had a method that returns a list of roots. So let's also do that for the PSO. let's call this PSO. We're just doing the method overloading because the return type is different. And everything is the same, a list of doubles. Okay, and here we just have to set PSO. And maybe I'm going to use this if condition here for the potential root. Okay, and a start is the start of the interval should be points I, the end of the interval should be points I plus 1, because when we find a root candidate in each sub-interval, we have to make sure that it remains in the sub-interval. Alright, so let's go and try to test it. So I'm going to create a new class, test PSO root, and I have a main method here, so I'm going to create a real root function. Func equals t goes to let's say, or x goes to x times x minus 1, and then we're going to create a real root object, and it's going to, let's call this, a good name or an appropriate name is root finder, new real root. And let's try to get the other constructor from a real root function, and then we're going to get the root, double root finder, PSO start -5 to 5, let's say, and then we're going to print the root. All right, let's see what happens. Nan. So it was not able to find the root in this interval. Let's go back here in the real root, and what I'm going here for the test, I'm going to do the math.a. okay, let's see, -2 to 5. It again returns nan. So let's see. Okay, set the minima is true, best value. Let's try to return the root also. So it returns 0. Let's see. Best value is 0. Let's have a look at the PSO that we had before. We set the minimum and see where is. I think I had this here too. Okay, so what we need to do is so what we're getting here, if you let me just put this here. So the mistake I made here, so the best value is the function minimum, which is basically 0. So what I need to do, I need to get the vector. So PSO best position. All right, and this returns a vector nd, n-dimensional vector, if you recall. And in the best position, we're going to, we know that this is an n-dimensional vector, and in the vector nd, if you recall, we defined a method at to get the component at some index, and this is index 0. All right, and then so this is where the vector is, the position of the position candidate is. So mean candidate in terms of the position. We were initially or originally we were returning the value of the function. So this is position. And then let's go here. Alright, now it works. It can find -1. And if you recall, we said that PSO is only able to return one minimum or one maximum, so it cannot find all of the extrema. Alright, and because it's a random. And one thing to recall, one thing to notice is that here -5 to 5 is not a bracket. So for example, if I apply bisection, this is going to fail, right? The bisection most likely is not able to find the root. It is in this case because we originally look at the two intervals, right? So even though this equation has a ±1 root, in this interval it's not able to find it. So bisection is most likely is going to fail. Now it has to fail, but the way we implemented it, that we don't check for the bracket originally, we just divide it in half, in two, and then search for each interval. And there is a high chance that if we have -5 to 5, -5 to 0, and 0 to 5, both of them are brackets. So that's why our bisection method is able to find. So that's a little bit of enhancement to the original bisection. But in general, because this is not the bracket, the bisection is going to fail. And as you can see, if you do this, then we have -2 and 1.5, 1.5 and 5. And none of them are brackets for the roots. That's why the bisection fails. But then the PSO doesn't care. So the PSO is able to find the root, and it's random because the functions, the original particles are random. And it doesn't care about the interval either. So it's still able to find it, -2 to 2. It finds it, no problem, -2 to 1. It finds it, -1 to 1. It's not able to find it. That's because we didn't add the test for the start and end value. So let's go and do this too. So for the start and end value, we're going to check the start and end in the beginning. Now it's able to find it, and it checks the start value first. And it can find it, so no problem here. And let's try the list one. So a list of double, let's call this roots, and let's call the root finder, and PSO with the list start -5 to 5. And we're going to search for 100 intervals, which is a bit overkill, but let's do it. And let's import the list from the Java util, and we're going to sys out on the roots. So this should return -1 and 1. No surprise there. Okay, let's remove this, and -1 to 1. And let's change this function a little bit more. X cubed -1. So this only has one root. Okay, let's increase this to -10 to 5. Still one root. Pretty fast, very convenient. And another thing that is interesting about this PSO method in comparison to other methods is that this is not recursive. So PSO method for finding roots is not recursive. All right, we're not looking at any recursion or anything, so we're not dealing with the method stack and the calls to method stack that happens during any recursion. Okay, and therefore it tends to be more optimal in terms of there is no recursion happening. All right, but you have to make sure that you do this final test. So you run the optimization, PSO returns some number, and then you test that number is in fact the root or not. All right, and let's do our tangent thing to make sure that PSO does not have any problem with the root being tangent. So we know that x minus 1 squared has a root at 1, but there is no way we can find a bracket, right? So let's see. It finds 1 with no problem. So let's try bisection. We're going to return a root or the list double roots bisection equals root finder bisection. We're going to return a list here. Start is -10 to 5, 100 subintervals, and we're going to sys out the roots bisection. All right, let's see. Yeah, so the bisection fails. We can do trisection. Still fails. We can do other methods. Secant, -10 to 5, 100 subintervals. Secant fails. We can do Brent. Now we have a lot of hopes for Brent, so Brent most likely can find it. Let's see. Yes, Brent is able to find it. Let's test Newton. This one returns a list. Okay, so -10 to 500 intervals, 1000 max iterations. Let's see. Newton is also able to find them, but then the accuracy of the Newton and Brent is not exactly at PSO. This shows that the PSO is in fact converging faster than the Newton, and that's because we had 10 particles. We set it to 100 iterations, so we're looking at 1000 possibilities, which is way better than this 1000. I mean, at least for Newton is also the same, max iterations 1000. All right, and let's go back here. We had these test all methods, and we had this polynomial x squared times x minus 2 squared times x minus 3 times x minus 4, and the only method that was able to find all these roots, we had 2 tangent roots, x0 and x2, and 2 simple roots, and the only method was Brent was able to find them. So let's do test PSO here also, and let's comment the Brent out. Okay, and we're going to implement the PSO. Test PSO, and in the PSO we're going to call the PSO method that returns a list, and the interval was -1 to 6 with 100 subintervals, and we're also plotting it, so we're plotting all the roots. All right, so let's see. We have 0, it's a tangent root, no problem for the PSO, -4.96 10 to the -18, so it's 0. And then we have one root here at 2, no problem, it's also a tangent root. We have one simple root at 3, no problem for PSO, and 4 again, so PSO has no problem finding these. And if we compare it with something like trisection, it's not able to find the tangent roots. All right, so again, a minimization algorithm helps us a lot in terms of finding all the roots, and the fact that we don't care about the behavior of the function that much. We just take an interval, find a minimum, a candidate for the minimum of the function in that interval, and then test whether or not that minimum is actually the root. But then in order for this algorithm to actually work, we have to make sure that instead of testing or instead of finding the minimum of the function, what we are actually going to find is the absolute value of the function. So the fitness function that goes into the minimization is actually the absolute value. All right, that guarantees that a root is the minimum point over the interval when the function crosses the horizontal axis. All right, so thank you for listening, and I hope you enjoyed this, and I'll see you in the next video.